So this is the Chapter 1 Toolbox. The toolboxes of each chapter contain the ideas and skills that you should already know prior to this course. So these would be materials that you worked on in your prior courses, such as Algebra 2. And I know a lot of this also was covered in Algebra 1. So you are to read pages 1 through 7, look at the examples, and then do problems on page 8, 1 through 33 odd. So the first big idea is the idea of sets, and sets are very important in mathematics. Here I've written down two sets. One is set A, which contains the elements 1, 3, 5, and 7, and set B, which contains the set of all numbers x such that x is an odd number and x is greater than or equal to 1. And so this would be very similar sets, except for the first one, A, stops after 7, and whereas this second one, if I could rewrite it in this way, I could say 1, 3, 5, 7, 9, dot, 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 and then you could use your inductive reasoning to assume that it kept going with each of the next odd numbers. So there's various ways that you can describe a set. Sets need to be well described. What do we use sets for? Well, we're going to use sets to describe the domain and range of functions. So we're going to be using them to describe the domain and range. Some notation that you might need to be familiar with is there's the empty set. This is the set that contains nothing. Sometimes it's written like this with two brackets with nothing in them. We talk about the elements of a set. So for example, 1 is an element of A. 1 is also an element of B because it's in both sets. But if I look at 9, 9 is not an element of A because it does not. 9 is not one of the members of the set A, but 9 is an element of the set B. So there we have sets. So some special sets that we're going to be using are in the real number system. And we represent real numbers with the capital R with that extra line going down. Some sets that are in the real numbers that we cover in Algebra 1 that you should be familiar with are the natural numbers, which are the counting numbers, 1, 2, 3, 4, etc. Also the integers, which we represent with Z. So that we would have the natural numbers and their opposites and 0. So we might represent this as -2, -1, 0, 1, 2, dot, dot, dot. Then we have the rational numbers, which we represent with a Q, not an R, because R is used for the real numbers. And this is the set of all numbers that can be written. So it's the set of all x such that x can be written as the form P over Q, where P and Q are integers. And of course, Q can't be 0. And another way to see these numbers, if they're rational, is that if you divide them out, if you divide that ratio out, you're going to get either a repeating decimal, which means that you'll get a number pattern that you'll be able to see, or you will get a terminating decimal, which means the decimal representation will stop. Okay. The other kind of number, of course, is irrational numbers. And the only kind of irrational numbers that you need to be aware of and would be pi, the constant e, which we'll talk about when we do logarithms and exponents, and then also any square root, or actually any root that's not a perfect root. So any square root of a non-perfect square. So it might be the square root of 2, square root of 7. Not a number like 4, because the square root of 4 is the integer 2, but anything else that does not make a perfect, that's not a perfect square, would give you an irrational number. And contrast that to repeating and terminating. If you look at that decimal expression, it will not repeat and it will not terminate. It just goes forever without a pattern. Okay, of real importance to us is interval notation. So we're used to representing things on a number line or with inequality notation, and I'll refer you to page 4 of your book to look through more examples of this, because we will use this a lot and it's useful. It's a very compact way of representing something, so it's efficient. So if I have something like x is greater than or equal to 5, of course we could represent this on the number line like this. We could say, here's the number 5, and it's everything bigger than that and including 5. So I used a closed dot. If I had x is greater than 5, then we would have the same graph except for we'd have an open dot, right? Well, there's a couple other ways to represent this. One is we can sometimes when you make this graph, we make it, instead of a closed dot, we do a square bracket. Instead of an open dot, we do a rounded bracket. And this gets to how we represent using interval notation, is that we would represent this with a square bracket 5. This does not stop at any particular number. It goes to a very big number, which is not specified. So we use positive infinity. And of course, infinity is an idea, not an exact stopping value. So we use a round bracket for that. And of course, the other way we would have this would be 5 to positive infinity. So this is the interval notation that I have in green, and you're going to have to be able to understand and interpret what interval notation means. It's really not hard, it's just different. And so you might have something, an interval like this that says -7 to 9, and you'd have to know that this does not include 7, does not include 9. If you were going to graph it, it would look like this. You'd have -7, and then you would have 9 up here, and then it would be filled in the middle. So 9 is not on this graph, but 8.9991 would be. So it's everything smaller than 9. So that's the idea of interval notation. Square brackets mean the endpoints are included. Round brackets mean that it is not. There's many examples in your book on page 4. So we deal in algebra with algebraic expressions all the time. It's just a combination of variables and numbers that are added, subtracted from each other. And so a couple of vocabulary terms we need to remind ourselves of is that the number in front of the variable is called the coefficient, and the number that is all by itself without a variable is called a constant. So a very important type of algebraic expression is a polynomial. Poly means many, and nomio means numbers, right, or representing. Of course, polynomials contain variables as well. And so a polynomial has many pieces. There are pieces that are added or subtracted from each other. You might have something like 5x cubed plus 2x plus 1. That would be a polynomial expression. So what makes it a polynomial? Well, let's talk about what it makes it not a polynomial. So if you have something where you have a variable that's in the denominator, then it's not a polynomial. If you have something with a negative exponent, like 3x to the minus 4, that is not a polynomial. If you have something with a fractional exponent, like 2x to the 1/2 power, or 2x where there's a square root of x, those are not polynomials. So polynomials have positive exponents, and they are added or subtracted from each other each term. These are called terms, the pieces, and then together they make up the polynomial. The last bit I'm going to talk about are subscripts. Subscripts are useful because they allow us to make variables that look similar but are different. So for example, if I want to use the variable x, I might choose to have two different ones, x1 and x2. If I do that, these are as different as using x and y because they're different. X1 is not the same as x2. But the fact that I'm using an x might be reasonable. So for example, if I was looking at linear equations of the form y equals mx plus b, I might talk about a particular x. So I might go y equals mx1 plus b, and then, or actually y1 equals mx1 plus b, and then I might say y2 equals mx2 plus b. So these are different equations. The variables are not the same, but I'm using them because of that form y equals mx plus b. The that form of a linear equation. I might want to keep it with an x1 and an x2. So that's a choice that people make. It's something that you should be aware. Okay, so your book assignment is on page 8, numbers 1 through 33 odds. I will be looking them over for accuracy, and then we'll talk about any problems that I see as a pattern or that you have particular questions on.